Okay, so our first speaker of the morning will be Roberto Fernandez, who will begin to give us an introduction to cluster expansions, which are a tool from mathematical physics that I think will be very useful for combinatorialists.
Thanks, Alan. So, in fact, I am three people at once. On the one hand, I'm substituting for Christian Borgs, that unfortunately couldn't come, so I will try to present some of his results too. And also my collaborator, Aldo Procacci, with whom I have discussed all this stuff and couldn't have been solved without him. So what I plan to do is, in this first hour, really give you an introduction from scratch to cluster expansions. I'm assuming nothing. And I will try to be honest with you on two accounts. First, I'm not going to disguise the fact that I come from statistical mechanics. So I won't try to disguise. I'll try to lean towards notation motivated by statistical mechanics that can be translated into graph theoretical notation. I will mention it. But I cannot help it. I will probably all the time come back to the statistical mechanical notation. On the other hand, also, I will not disguise the fact that the motivations and the questions are statistical mechanical questions. So I will present you the questions, even if they have not direct bearing on what you are interested, but at least will give you an idea of why they were developed and what type of things they are expected to do, this cluster expansion. Okay? Now, that will be the first hour. And in the second hour, then we will get into really technical, but not very technical stuff on convergence criteria, which is the thing that interests us. Okay, so I'll give you the general setup for this cluster expansion. What is the goal in this general, this hardcore setup? So you want to study systems formed by objects, whatever the objects are. Okay, this is very general, that are constrained only by some non-overlapping, some exclusion condition. Okay? So what are the ingredients of a cluster expansion theory? You need first a countable family of objects, which eventually could be vertex of a graph, or that they were called, they received different names. In the initial theory developed by Gruber and Kunz, they were called polymers, which is an extremely badly chosen name, but it stuck. So I will use it. Dobrushin proposed animals. Other people used some particular animals, like bees or foxes or something like this. But okay, whatever the name, this is our basic family.
And graph theorists would say vertices.
Vertices, yeah. Okay? But as there will be several graphs appearing, that could also be misleading, because there may be graphs at different levels. Okay, now these objects are characterized by some incompatibility constraint. You have to be able to say when two things are incompatible. Okay? And then I will provide some examples. And the notation is, for incompatibility is this one, and for compatibility will be without the negation. And as Alan pointed out, this is exactly the opposite notation that you would use if you were in the graph theoretical framework, because if these are vertices, being incompatible means they are neighbors. Okay? So they will be connected rather than incompatible. And then the last ingredient is a family of activities. This is a family of weights, which for us could even be complex. Okay? In fact, for physics, this could be complex. For probability, will always be real. Okay? So this is just an assignment of numbers. And then, so this is the probabilistic object you are interested in. You define a probability weight. Given you a finite family of these polymers, the weight is what you expect, is the product of the individual weights plus the constraint that they have to be compatible among themselves, between themselves, in fact. And then you normalize to make the whole thing a probability. Okay? So for every finite family, you give these weights. So the normalization takes this form that you may have already perhaps seen, and it's called partition function for this system. So you just sum over all the possibilities of the numerator over all possible n's. There is this n factorial that appears because in here I am considered ordered n apples. If I would take just the set of gamma 1, gamma n, then this disappears. But this is traditional and is, in some cases is safer.
Roberto, you are always assuming that an object is incompatible with itself.
Yes.
So these gammas are always distinct.
It always will be distinct. This is not necessarily a lack of generality because it just amounts to resumming these constants otherwise. Okay, now, so this is it. Okay, you have these ingredients and you are interested in these probability distributions for every finite. So lambda is a prefixed finite family, and then you take for each n tuple inside lambda. Lambda is a family of vertices. Now, which are the questions? Well, you are interested in the thermodynamic limit. So you are interested in seeing what happens when the probability measure defined by these weights, you take the family lambda to go to the whole of P and see whether this defines a suitable probabilistic measure, suitable object. Okay, this corresponds to what is called thermodynamic limit in physics. And then you are interested about the existence and the properties of such a limit. Okay, that's the very original question. I mean, what is the motivation then? This may have been said already, but in physics this corresponds to a grand canonical ensemble of a polymer gas. It's a gas because these things do not interact, except for the exclusion. There is no interaction energy potential related to how far they are or not. They cannot overlap, that's all. Now, it also appears in statistics. These are invariant measures of the so-called point processes. Okay, processes in which there are some seeds that appear with Poissonian clocks, and then they could survive or not depending on whether there are other seeds with their grains around them. Okay, so I'm not gonna, just for information, so it appears in several settings. Now, a less immediate motivation is that, in fact, when you do statistical mechanical models at extreme situations, high or low temperatures, you almost always can map the models into one of these systems. So if you understand these systems, you understand a lot of statistical mechanics. In fact, there is kind of a meta theorem that if you try to do a perturbative argument, somehow you fall into a map of this type by choosing the right variables, which may not be obvious in any case. Okay? And then, of course, all the business of the zeros of the partition functions, which in statistical mechanics are related to phase transitions, and in here they have other interpretations. Now, if you want to write the whole thing in graph theoretical terms, then in fact you are dealing with a graph, let's call it interaction graph, whose vertices are the polymers, okay? And the edges are the incompatible pairs. Okay, so instead of this notation, if you prefer, imagine this notation. And you are dealing with vertices and neighborhood. Okay, so this is a contrast that negation there and non-negation there. Now, this is a pretty general graph. You have to be ready to deal, if you are interested in the physical applications, with situations of infinite degree, okay, which is common in low temperature, high temperature physics. Okay, so the polymers are incompatible with infinitely many other polymers in general, or you have a graph where vertices have an infinitely many neighbors.
But Roberto, in fact, you only consider the induced subgraphs on finite lambda polymers. So you don't really have to deal with the graph of infinite degree. You have to deal with graphs of arbitrarily large finite degree and try to get bounds that are uniform.
Yeah, that's the approach. Yes. But there is an underlying target graph which has infinite degree. But you don't deal. That's the statistical mechanical point of view. You never deal with infinite all at once. You go through finite windows. It's reproducing experiments in a sense. Okay, and here too late I say what Alan already pointed out, that for simplicity I consider polymers to be incompatible with themselves. Okay, now one simple example, if you just to give you some direct geometrical example of this, is the so-called loss network, where think in a set like ZD, and the polymers will be just vertices of ZD, which are going to be connected. Trajectories in CD. So some subsets that connected that correspond to calls, communications between points. And if the model is probabilistic, okay? Each possible call, a call is a polymer for us, can happen with some Poissonian rate, but it can only be established if there is no existing call using some of the connections that it needs. And once the call is established, it lasts an exponential one life. Okay? This is a model in statistics, which is important for applications. And then for this model, it's exactly the measures that I'm calling basic measures, the ones I wrote at the beginning, defined by this weight omega, are precisely the invariant measures for the finite region process. And when I take the thermodynamic limit, I am going to questions like the existence of the infinite volume process, okay? the real process, the loss network process. But there is a less immediate example, which is lattice models in statistical mechanics. So let me just define you what is the lattice model and I'll give you an example. So how do you construct a lattice model? So first of all, you have a lattice. A lattice is a countable set. We are not going to, well, in what I'm going to say, we don't use the fact that it need not be a lattice in the mathematical sense with partial order. But you may think in ZD, that's good enough. Now, at each point of ZD, there will be some space, which less single site space. The points in this lattice, let's call them sites. And this space has everything you need. Typically, for instance, it could be finite space. Then you will have the operation of summing, which is the counting measure. But it could be the unit sphere, and then you have a measure, which is a probability measure, like the Borel or the Haar measure. Okay, and then you construct the product structure. So these are copies of this space E, one at each side. And you construct these Hamiltonian functions. First, you define what is called an interaction. This is a family of functions that depend only on finitely many sets that more or less correspond. You can think this is the energy contribution of a given collection of spins at the sides. Okay, the way I'm going to use the word spin, you could call them pixels if you want. So for each configuration in this family B, the function gives you an expression for the energy. And then you construct the Hamiltonians, what you sum for all the B's that are in your region. In fact, this is wrong. This is B intersection lambda different from empty. But it's not enough to sum the ones that are in the region. You have to also consider boundary conditions. Okay, so what is, you have a finite region, and is there some chalk here? Yeah. You have a finite region lambda, and then you construct all the bounds. So in here, there is some frozen configuration sigma, and you think this is a function of what happens inside the region. Once you have that, then you construct your probability weights by the Boltzmann prescription. Okay, so you use the exponential. There is this beta factor, which is interpreted as the inverse temperature, and the normalization, which is just the integral of the numerator with respect to all possible omegas. The sigmas are fixed. Okay, so this is called the partition function. This is a funny way of writing, for instance, the sum over all spins, if it is finite. Okay, so this is the setup. For instance, the canonical model is the Ising model. In the Ising model, you have lattices ZD. You have only two possibilities at each side, arrow up or arrow down. And then you have only contributions from pairs of neighboring sides. And the contribution is just the product of the spins, the values at the side. So this is something that is, the minus is for historical reasons. So this is minus G if it is, the product is 1, so if both are aligned, and it's plus G if not. And let's think in G positive, the ferromagnetic version, for instance, that would mean that energetically it pays to be aligned. Now, to map this into one of our polymer models, we do a change of variables. We go from the spin variables, from the omegas, to some non-local variables, which will be contours, which will be the polymers for this model. And you do it in this way. Suppose that G is, I'm talking about the ferromagnetic, so let's take the G positive, even if I don't say it here. J positive, sorry, that's the French. How do you count? Suppose that you take plus boundary conditions. how do you count the energy? Okay, well, for each aligned pair, you have a minus g, and each misaligned, each frustrated pair, you have a plus g. So there is a 2g jump for each, 2j again, sorry, for each pair that is frustrated. So you can express the energy in this way. Over a background of minus j for each bound, for each pair, you add 2j for each frustrated pair. And then you get the total energy. This is with plus boundary condition. I fix everything plus over there. Now, when you replace this in the exponential of the Boltzmann factor, the n lambda part does not depend on omega, so the exponential is a factor at the beginning. It's also a factor here in the normalization. It goes away. So you end up just counting frustrated pairs. And to count the frustrated pairs, you do this geometrical construction. What you do is you place this is your lambda. So suppose that you have a thing like this. You place a dual object. So if it is in 2 dimensions, it will be another segment midway between frustrated pairs. If it is in more than 1 dimension, it will be a plaquette. And as you can see, these things will produce closed surface or circuits, which it could be, you will have several of them, could be nested, and you can decompose them into maximally connected sets in the obvious sense. Okay? Without entering into subtleties on the precise definition, but just get your idea. This will be a contour, this will be another one, another one, another. Okay? So one of these maximally connected surfaces is a contour. Now, what are the properties of these contours? Well, they have to be disjoint, because if they touch each other, they will be part of the same contour. And you have a one-to-one correspondence in this extremely favorable case between configurations and families of contours. Okay, if you give me these families of contours, I start from the outside, that is all pluses, and each time I find one surface, I change the spin, I flip. I go minus there, I go minus there, then here I have to go plus again, etc. And I reconstruct the configuration. Okay? And the contours give me an easy way to estimate the energy, because each segment of the contour is one frustrated bond. Right? So by summing all the segments, so the length of the contours gives me the total energy multiplied by 2b, 2 beta g, j. And here you have this factorization property that I have, given that this is exponential of the sum, each contour has its own energy attached, its own weight attached, and there is no other relation between the contours, no other interaction, other than they have to be disjoint. Okay? So I recover, these are my weights. The compatibility constraint is hidden in this symbol here, because I'm saying that it's an allowed family of contours. And this is explicit expression for the normalization, this normalization partition, and okay, which I wrote is exactly the same as before. So this is a typical example of a transformation that allows you to go from some statistical mechanical system into one of these polymer systems that are dealt with cluster expansion. Okay, so these 2 models that I just presented, the one of the point processes, these seeds with grains, and the low temperature is in model. This is good at low temperature. Sorry. This is good at low temperature because it's there where these weights are smaller. Okay, contours appear only rarely, and there is where I will have conversions and everything will go fine analytically. So these 2 ideas we put together defines a particular family of cluster models, of polymer models, which we will call it geometrical polymer models, which historically were the first to appear. But they're a particular case in which the polymers are sets of points. Okay? So you take, there is an underlying set before it was the lattice. In fact, the dual lattice here for these models. Okay? And then you take, as polymers, finite subsets of V. So the letter V is because you can think them as vertices. again. You have activity values, and then compatibility is non-intersection. Okay? Now, that's all.
The activities, there's a typo. It's not gamma in V, it's gamma in P.
Gamma in P, yeah. Yes, thank you. Yeah. The V is the basic thing over which the P's are
Because
defined.
this is where the terminological confusion sometimes comes. There are two levels of vertices.
Yeah,
right?
that's why I avoid vertices for the
The
other.
vertices of the underlying graph V in a geometrical polymer model, and then the polymers, which are finite subsets of V, are the vertices of
For the cluster
this
expansion.
polymer graph.
Yeah. This is what I call interaction graph. So that's why to keep them separate, at least in my mind, this I could think as vertices of a graph at this level. But for the cluster expansion, I think in polymers and compatibility and incompatibility, and I don't keep the graph theoretical approach there. But you can keep it at both levels if you don't get confused. Okay, so these are the geometrical polymer models which will provide. In fact, for instance, these are the models that are of interest for the chromatic polynomial. Now, partition functions. Why do you insist in partition functions? Okay, so there is this obsession with partition functions or log of partition functions that you can see in statistical mechanics. And I give you three reasons why it is a reasonable thing. Okay, the first two are probabilistics. Okay, first, if you are interested in cylindrical events, I'm going to define it in the next transparency. Then these are ratios of partition functions. If you are interested in central limit theorems, the moment generating functions are also ratios of partition functions. And finally, there is an independent life for the complex zeros of the partition functions, which in physics are related to phase transition thanks to Yang and Lee theorem. And for instance, in coloring problems have a different interpretation. So in more detail, what are these cylindrical polymer events? You take these basic probabilities in some finite family of polymers, and you take a subfamily of polymers that are mutually compatible, otherwise they couldn't be there, and you ask what is the probability that they are present. So if they are present, then the weights have to be there, and then for the rest of the polymer space, you can put anything whatsoever, as long as what you put is not incompatible with what you have to have. So this is this notation here. Okay. So if you want, in graph theoretical term, you are excluding the neighbors of this gamma 1, gamma k, besides the gamma 1, gamma k. So, and here you see, this is the ratio that interests you if you really want to estimate these probabilities, especially in physics you want to estimate what happens when lambda goes to infinity. Now, if you are interested in central limit theorems, typically what you do is you define some function of additive functions of the polymer, and then you ask for the expectation of the exponential of this function multiplied by a complex parameter in general, okay? Because you are playing with the characteristic function. Well, if you do this, this is the expectation with respect to this polymer measure. You just have to weight the values of this function by all the possible weights and normalize. And then you see that this is, again, a ratio in which you have the same compatibility constraints. It's just that the weights have changed. They have gained an exponential, an extra exponential. But it's, again, a ratio problem of partition functions of a polymer system. Okay? So, and the third thing is what you have heard more in this talk. You have this object, which in physics is called the free energy or the pressure, depending on the signs. That if you could put a minus sign, it depends on what the system represents. It is known that for reasonable, under reasonable hypothesis is independent of the boundary condition. And then in physics, you wonder about how smooth this function is with respect to all the parameters in the game. I put beta there, which always is always there. And this boldface letters means vectors. This is a family of parameters that could be there. In easy models, sometimes you add a magnetic field. In more complicated models, you could have several fields. Okay, and you wonder is how smooth this is, this limit, with respect to these parameters beta and h, because you have this meta theorem in physics that functions should be analytic unless there is a good reason. If it is not analytic, then something interesting is happening. Okay. And then you may wonder what are the sufficient conditions for an analyticity of f. And for instance, this is basically this is equivalent. If you can prove that all these partition functions have its zeros in complex sense uniformly bounded away from a given set of values, uniformly in the volume, then when you take then this log can never as the partition functions themselves are analytic, then the free energy will remain analytic in the limit. Okay, and this corresponds to a radius of analyticity of these objects, which are independent of the volume. Okay, now, so the problem is clear. You have one of these exclusion problems, polymers, whatever the polymers are, depending on the application, with the exclusion rule, and you have the corresponding partition functions. And you are interested in ratios or in logs, and well, how do you control them? You want to go to a limit, so analysis enters, it's not just combinatorics. And there are different, there are two lines of attack that I could measure. Here we have seen, I could present, here we have seen one of them, which is the first one, that's the physicist one. The idea is to control through expansion techniques. And this will give rise to the cluster expansions, as I will mention, I will introduce it in the sequence. Okay, and this has several reincarnations. There are other expansions of the same type called Meyer-Virial, high temperature, low density, which are particular energies. Now, the problem with this line of attack is that not everybody likes it, okay? Especially Alan Sokal never liked it. So, okay? And so he used it, I mean, he never liked it till he had to use it, okay? And then he managed to use it in a way that avoids expansions. So I'm aware of that, okay? So, but I will try to convince you that sometimes it's not that bad to use expansion. Okay, now you have to, but of course to control the expansion coefficients, you have to enter into some algebraic and even graph theoretical tree type of considerations. And if you give a talk like this to a purely probabilistic audience, it is utterly unnatural because here the expansions are controlled in such a way that you get analyticity. So it's much more than what you expect. In probability, you don't care about complex values. Well, that's not totally true, as I show you in the case of the central limit theorem, because if you go for characteristic functions, you do have to care a little bit about complex values. Okay? Now, there is an alternative approach for probabilists, which is based on this idea that they are basically point processes. So you can import techniques used to deal with point processes. Okay? Now you obtain weaker results, like existence of these measures in the infinite volume, but no analyticity, but of course under weaker hypothesis too. So in some cases it could be useful. You have the advantage that there are a whole bag of tricks that you can import, in particular this notion of coupling in probability, which is extremely fashionable, and it even leads to perfect simulation algorithms, which is a thing that has not been yet fully exploited. So I don't think I will have the time to show you this, besides it's beyond the point probably for this audience. So I'm going to insist on the first approach, okay? Dealing through expansion measures. So what is a cluster expansion? The idea is very, very simple. You take this object, which is your basic object, because you are going to use it one way or another, either because you are interested in the log or because you are interested in the ratios. But that's your object, okay? And what you try to do is to write it as a formal exponential of another series, okay? This is formal, so namely you just, if you want, you take, what you do is you propose a series like this, you know the expansion of the exponential, and you want that these two things be equal, and you establish some algebraic relationship between the coefficients of this development and the coefficients that you have here, which are there and there, as a
Another
power
way of
series.
saying it is you have a formal power series that starts with 1 plus, so you can take its logarithm.
As a formal power
That's a
series.
formal power.
But yes, but for a change, I prefer to see z as the exponential than rather the power series as the log of z, because of what I'm going to say in the sequel. Sometimes it gives you, but it's completely equivalent, no? But sometimes it gives you a better hint of why this form is particularly useful. Okay, so this is, at this point, it's just an algebraic problem. Okay, how you can obtain these coefficients so that you have an identity between these two things. Okay, purely algebraic. Now the coefficients are called the Ursel or truncated functions of these polymers, and they are symmetrics in the gamma 1, gamma n. A cluster is a family of these polymers that has a non-zero coefficient. Okay, and then the only thing so in this first hour you won't see the expression of the coefficient. I'm not going to insist. I just want to show you what you do with these coefficients. Next hour is going to insist on the coefficient. But I ask you to retain only one information. That cluster has to form a connected graph with respect to neighborhood or respect to incompatibility. Okay, that's one thing that comes from the algebraic analysis between these two things. Okay, now we are after ratios of partition. So by telescoping, if you take ratios between partitions of two different families, you can do it one by one, adding one polymer at a time, and then you telescope. Okay, so the basic object would be the ratio of two partitions in which you add one contour, here gamma 0, in one of them. Okay? Now, the top partition is the exponential of the sum over all possible clusters in lambda. The bottom is the sum over all possible clusters in lambda that do not include gamma 0, and they are in the exponential. So if you write this as the exponential of the difference, you are left with the sum over all the clusters that do contain gamma 0. Okay, so this first time you see why the exponential is more in. Okay, so this is written here. One of these elements here has to be gamma 0. Maybe it may be several, because once you go to truncated, then the exclusion condition doesn't hold anymore. Okay, so you could have an arbitrary number of copies of gamma 0 among the things. But now it is important to keep this. Now it's no longer the same to put. If you try to put curly brackets there, then watch out with the combinatorics. Okay, now there is a slightly more convenient series which is totally equivalent. That is like a limit of the ratio is the derivative of the log of z lambda, which is just a reorganization of the series in which you see what I do now. I don't have this somehow annoying condition that one of the gamma i's have to be gamma 0. Gamma 0 is one of the coefficients of the truncated, but you see the truncated function has one more argument than the product here. It's a simple exercise to show that if you take the log of z lambda, so the cluster expansion that I put before, and take the derivative formally, no worrying about the conversion, then you end up in here, in this expression. So I'm going to concentrate on that. Okay? And as we're interested in going to lambda to infinity, and also to have some ability here, so we worried about conversions of such an expression. Okay? So that's the difference with the algebraic community. I mean, we do worry about conversion. And let me classify the strategies to deal with these conversions in two types. I call it classical because it was the original one, and then the inductive, which is the one introduced by Koteski and Price, and you may have seen some of it last week. So what I do is to, in the classical cluster expansion strategy, what you do is you put absolute values throughout the different terms of the series. So you put absolute value there, and you put absolute value in z, which could be complex z, as I told you. Okay, so rho is replacing, it's an absolute value, so it's a positive thing. So if you are able to find convergence criteria for this series, then you have an absolute, and listen, another thing, here there is no lambda anymore. Here I'm in over all possible points. So if you are able to some convergence of this series, where there is pinned on gamma 0. So this is 1 for each gamma 0. Then you get a very strong notion of conversion for the cluster expansion, because they converge absolutely for all z's whose absolute value is less or equal than the rho, and then converge uniformly in lambda, because lambda is going away there. Okay? So this determines a region of analyticity that is common to all volumes. Okay? And within this region, the series, the formal series, becomes actual series, converging series, and you can, if you are interested in the ratio after all, then you can integrate this derivative, and then you have bonds like this. Okay, and here they are. Okay, now the consequences of that is that no phase transitions in this region. Moreover, you have very explicit series expression for the free energies and for the correlations there. You have like mixing properties like this. You have the central limit theorem. You have everything you want. You have absolute control. Let me go quickly, for instance, for the free energy. What do you do? Well, now for the free energy, let me take the case of geometrical polymers. So this factor of 1 over lambda, it corresponds to fixing one site in your geometrical lattice and asking that the cluster touches this site. So this is the expansion that you get, formal at least. But if you have the convergence, this is an actual expansion. So you can even compute it to a certain order. For instance, if you know that, okay, this is something I'm going to tell you in the second hour. For one polymer, the value is 1 of this truncated function. For two, the value is -1 if they are incompatible and 0 otherwise. So for instance, you can write this expansion as the sum over the polymers that touches 0 of the n equal 1 term. For n equal 2 is here. Okay, I forgot to say that they have to touch 0, plus a correction, and then this is a complete expression, and you can use it to extract thermodynamic information to compare, to get stability, etc. Okay? So you can do the same thing for correlations. Okay, remember these things there. Okay, now everything is absolutely legal because you have conversions. In the top, you have to sum over all the clusters that are compatible with gamma 0, that are in lambda but are compatible. In the bottom, you take overall. So when you do the simplification, you end up with all clusters, exponential of all clusters that are incompatible with gamma 0, and here is your expression, explicit expression for your probability. Okay, well, let me go fast here. Is not for me. Now, what is the other strategy, which I will review very briefly in the next hour? It's an extremely nice approach, the inductive approach, in which the idea is to find conditions on this z, or on the rho's, the absolute values, in fact, such that the fact that a partition function without a contour, without a polymer, is not 0 in a region, implies that adding the contour, you remain not 0 in the same region. Okay? So what is the advantage is that there is no mention of an expansion in principle in such method. It's just you can get away without really knowing that there is an underlying expansion. Okay, so this is Dobrushin call it no cluster expansion method. And of course, in any way you are proving the convergence of the expansion, so you can then use the fact that you have the expansion somewhere and use it. Okay, now there is a problem with this approach. A problem for me, not for Kotesky price, is that it looks like a miracle. I mean, here come these conditions, and they work. And then Dobrushin came and gave a little better condition, and it worked. Can you come with another condition? How do you come with another condition? Okay, that will be the first. There are more questions. Dobrushin and Kotesky price results were better than the classical ones. Why were they better? I mean, they were giving you less information than the full series. Is there an interpretation of what Dobrushin and Kotesky price, the condition they are proposing in terms of the classical approach? Okay, that's the questions we pose ourselves with Aldo. We spent a whole year of long, chaotic discussions, going back and forth with the different directions. And, well, we revisited the classical theory, and that's what I'm going to present in the second hour.
And you could add that those of us who like the inductive approach can pose that question backwards.
Yeah.
can your improved version of the classical approach be reinterpreted in terms of the inductive approach?
In fact, this is even more dramatic. I mean, some people that are very fan of the inductive approach told us, unless you prove that the inductive way, we don't believe you. But and finally, we cannot prove it, and I don't know.
We didn't tell you that.
Maybe not explicitly. But it took some convincing. I mean, it's normal, it should, because we had a different point of view.
Surely write down the closed form expression that corresponds to the cluster expansion approach.
Yeah, I mean, the point is they have a proof of a beautiful theorem using the classical method that Roman and I tried hard to translate into the inductive method, and so far we haven't succeeded.
Yeah, and with Aldo, we think that the obstacle is essential. I mean, it should not be very inductibilizable. Okay, the condition, but we don't know. Okay, now to finish this first hour, once we have convinced ourselves that the basic objects are the partition functions, and in fact that we are after ratios in most of the time, or logs divided by lambda, then we can introduce a notion of another way of relating some models coming from somewhere, typically statistical mechanics, with polymer models. You just need that the partition functions be the same or with a constant that does not depend on the parameters in the game, in either side of the equation, that could depend on lambda. If you get a relation like this, then you say that the models are equivalent, okay? Because they will give you the same information, for instance, about analyticity. Well, you need this constant to have a civilized dependence on lambda, okay? But let's not insist on that. So I'm going to present two examples, one of which is of extreme interest here. And for that, there is only one mathematical step that will be used 2 or 3 times, which is very elementary, which is the following. Suppose that I have a family, some index set, and I had to multiply the sum of 2 things. Then you develop this as all possible products, in which you choose in some of the factors one of the terms, and in some of the other factors the other term. That means that you are going to classify, let's call capital A, the factors in which you are choosing the second. So you sum over all families of second choices, product of second choices, and for the rest the product of that's all. This is going to be used from left to right and from right to left in the future. Okay? And of course, for the empty set, you put 1 for combination. Yeah. Yeah. Well, but sometimes it's hard to see. That's what they're using. So, okay, so first let's go to the post model and see the relation to the chromatic polynomial, which you may have seen it, but anyway, I think that given this is introductory, it should be mentioned. The post model is a generalization of the easy model. So you take a lattice, any lattice, you could define it in any lattice, but let's think it's ZD. And now the space, instead of being 1 and having 2 values, 1 and minus 1, you take a value from 1 to q, okay? Where q for you could be the colors, okay? And okay, so you sum, the structure is that you sum over this. And the interaction is as follows. There is a coupling there, and if the 2 neighbors are have the same color, let's call it like this, then the value of the energy is 0. Otherwise, it's plus j. So it pays to be aligned also in this model. Okay, so of course, so you only have nearest neighbor interaction. If q equal to this goes back to the easy model. So there is the partition function for the post model. You have to sum for a finite volume. You have to find sum over lambda, and over all bonds you put this term. And then you apply to it this Fortuyn-Castellane trick, which amounts to this observation. You can write this exponential as the delta plus e to the minus beta 1 minus the delta. That's all. Okay, and then you rewrite it as grouping everything that has the delta. Okay, in fact, the delta it has 1 minus e to the minus beta. This you call p, and the rest will be 1 minus p. When you rewrite the partition function, so you have this, and then we use the distributive law, and then you choose, let's call B the families where you choose the second term. So there you are, the product, and then the product of the rest. And you still have to sum over all possible omegas. But then you use the fact that if you have a branch of deltas, when you sum over omegas, all the sites that are linked by the delta have to have the same value of omega. So all the connected components of these families of bond have to have exactly the same color. So the sum can give you only q values for that particular component. So you get q to the number of connected components. And this allows you to rewrite these pots in this way, in which some of you may recognize this is like a percolation model, in which P is the probability of having a bond open, and then this is having closed, except that there is this weight here, which makes it a dependent percolation. Is the probability of being open and closed is not independent. There is a weight that tells you what is better. Okay, then you do, to pass to the what I'm going to call temporarily the FK model, you do a further change of variable. You take out the factor, the products of 1 minus p of xy over everybody. So before there were, this factor was only for those that were not involved by the delta. So now, I'm sorry. So now these factors disappear for the sum, from the sum, and you are left only for pairs in this choice B here. So this is this C lambda factor that you don't care, because you are going to switch variables. I'm going to call Q and P and V new variables. So V is this combination. Okay. So you end up with this Fortuyn-Castellane partition function in Q and V, which has this form, where V's are a combination of the P's. And then you go to a polymer model. So what happens? Each choice of B, this choice of these bonds, defines a graph, whose let's call VI the connected components. The vertex sets of these components have to be disjoint. There is a compatibility constraint there. It's a geometrical compatibility constraint. And of course, the VIs have to make the VIs connected. Okay? And then you have this C of B weight, which is K. K was the number of components of the graph, plus the number of isolated points. Each isolated point is a component of its own. And the number of isolated points is the total number minus the sum of all these vertices that you have there, that you reorganize by pulling the lambda out, and then this, you write it in this way.
Wait a minute. The GIs, so maybe you should have said, for you, the GIs are the connected components that are not isolated.
Yeah, good. Yeah, because this is the B, the graph defined by only the B part.
V sub B are the vertices that are touched by one of the edges in B.
Yeah. Should have
GIs are all those connected components that have two or more vertices.
Yes.
That have edges. Right, that have edges.
Okay, so you put this back into, there was a Q to the CB factor in the cluster, in the Fortuyn-Castellane thing. And then, okay, this, there will be a Q lambda factor due to this, which is independent of everything, just depends on lambda, so I pull it out. And because of limitation of space, I pass it to the other side. And then what you are left is exactly a polymer model. Exactly, where the fugacity, this Z, is this expression here. Okay? It's a geometrical model. The polymers have to be disjoint. These are the geometricals are sets, the polymers are sets, vertex sets of a graph, in fact, and they have to be disjoint. And you have this fugacity, which is a little complicated.
There's a slight typographical error in both places where you see cardinality of V minus 1. There should be parentheses.
The parentheses, yeah, thank you. Yeah. Okay. Now you see that this has a 1 over Q here. So these things are very small if Q is very large. So this will correspond to a high Q expansion. Also, the V's are small when when beta is small, that is when the temperature is large, so it's also a little bit of high T for a physicist. But you don't care, I mean, for you it's an expansion. Okay? And this is related to the chromatic polynomials. I go quickly on this because, so there is this, I'm going to denote it PG of Q, so the number of ways of coloring G with Q colors, you're having a graph there, so that the two vertices don't have same color. Then you can write it that way. You sum over all possible coloring ways, and the constraint is that for nearest neighbors, you cannot be equal. Okay? Well, this is, you know it. And then a slight generalization, you change the -1 into a V. And this is something that you know very well under different names. And you rediscover here this what I call the FK partition function, which is the partition function for the post model after you have taken out this factor 1 minus P to the volume of, to the number of bonds. Okay? Which is related by this factor Q lambda with the partition of a polymer FK model, okay, which I just introduced. So according to our definition of equivalence, to analyze this, we can analyze this. Okay? And that's how partition functions entered into the graph coloring community. Okay, and it will be one of the important cases that I will discuss in the next hour. Okay, so this is what I have for the introduction. So I have still 5 minutes left, but it's a good time for me to stop. Yeah.
Are there any examples of polymer models which are not come from a graph? So polymers are sets of vertices of a graph, and they're not geometric. Or geometric means that I think that they're related.
There is an underlying, yeah.
Two things are related if their vertex sets intersect.
Yeah. Well, of course you can do.
They intersect in at least one.
You could do very sophisticated definitions of what intersection means. They could be, instead of intersection, to be a less than some distance, or you could play a little bit with.
Well, I was wanting to go the other way. I was wanting to say they're related if they intersect in at least two vertices.
Yeah, they need not. I mean, you could.
Well, that would be how I would say it.
You could say that if they are closer than something, then they are incompatible.
Bill wants to go in the other direction. He wants to say two polymers that intersect in either no vertices or one vertex are compatible, but intersection in two or more vertices is incompatible.
But it could be. I mean, this is totally general, yeah. But I have not seen such a system. But you can apply it. Of course, you can apply it.
The function fraction that is used to construct, you have some restriction for the form of the function fraction?
The form of which of the
Interaction, for example, between the polymers, for example.
well, the polymers in what I present, there is no interaction other than the compatibility, okay, or incompatibility, and the compatibility could be very general. So it's an all or nothing interaction. In terms of energy, it will be, if you want to write it as e to the minus beta h, the contribution is 0 or infinity. Okay, for this particular.
In contribution.
So a nice question would be to go into software models in which you have some interaction, not necessarily infinity, but for these models, what we did doesn't bring any improvement. So I'm not discussing it.
Most of what Roberto was discussing generalizes to the case where instead of having no interaction between polymers, you have an arbitrary repulsive interaction. So two polymers might be compatible, but there's some positive, some suppression of them both being there. And most of this generalizes, but
Yeah, except that
but
our
it's not
criterion,
necessary for these applications.
the new our criterion doesn't give anything new to Koteski price or Lagrangian criterion in that case. Yes.
At some point you had a quotient of two partition functions where you added 1 gamma 0.
Yeah.
And you called this cylindrical. What is the meaning of cylindrical?
No, cylindrical is the probability. The probability is cylindrical events are events in which, in this product structure, you only ask for what happens at a finite number of sites. Okay? Because you have a product structure.
Okay.
So if you, it's like having several accesses and you only restrict some of the coordinates and the rest are free. That's why I call cylindrical. I'm importing nomenclature from probability. I'm sorry. No, nothing deep. Yeah.
I have just a comment on the question earlier. I mean, there is a version where it's edge connectivity, multiple edge connectivity, which intervenes, and you have cluster expansions in terms of k-connected parts.
So like multigraph or something like this.
I'm sorry, this is where the polymers themselves, I mean, where does K-connected come up? Does it come up?
It's in the-
You have the polymers, which are themselves subgraphs of something, and then the compatibility constraint involves
You would have, if the polymers would involve instead of having their activity given by a sum over trees, you would have a sum over two edge connected subgraphs.
So this is in the activity of the polymer.
Yeah.
in the activity,
Yeah.
and the compatibility condition is still just disjoint.
You would have this joint and you have extra structure between these components.
But inside each polymer. So the structure is inside.
No, going outside, basically, some loose one particle reducible parts between these blocks which are two connected.
So this may be worth pursuing because this may be going in the direction that Bill was trying to go.
Because sometimes you need to have one line doesn't give you enough decay, so you need to have two. And I think there is a paper by Rivasso and Affichin and Magnin on the Hubbard model in condensed matter, where they use this type of thing, and they use twice Menger's theorem in the vertex version and in the edge version to show that there is enough decay to show that some two-point function converges.
And Atlas Semazi was doing it. One particle, two particle irreducible structure.
Yeah.
Okay, so I have another comment on that. So I don't know what the thing you refer to now, but going back to your original question of having, just thinking of two polymers with a single common vertex as not, or what to call it, not interfering. I think there's a problem there, which one should be careful with. Suppose you have three different vertices, and you have three polymers, each one of them including two of these. Then the intersection of any pair of them will just contain one, so they will be independent. But if you look at set all three of them, you would expect them to be dependent. It's just, since I'm probabilist, it's just a usual probability theory of pairwise independent events, but they are not mutually dependent, all three of them. So one has to handle that
Yeah, it
situation.
would force you to look at a hypergraph version rather than a graph version.
Yes.
So like you say, you would have large dependencies.
Yes.
To be discussed. Yeah. Okay, coffee time.